Welcome back. I am checking our stream, making sure that we're ready to go, and then we can take a look at project number 1 with our first kind of numerical methods sort of thing. Looks like we got video that we're ready to go, and then we can take a look at project number 1 with our first. And I'm still on. Yes, we can numerical methods sort of thing. Looks like we got. So we're good to go. Cool. All right, here we go. All right, so in the first getting started project, it seemed like people were getting the hang of using Python as a calculator and even using some Euler method. Maybe even grabbing, here, we'll go over to Copilot. Let me pull this up. Oh, am I signed in? I want to sign into my, how do I sign in? There we go, sign in. Microsoft, here we go. So I don't have any bias towards Copilot. It's just, it is an enterprise version of an AI system that seems to work pretty well. It works well enough, right? So let's say learn about a topic. I need to know how to create an Euler integration in Python. And so I'm pulling this up because I saw code that looked like it was kind of AI driven and gives a little bit of background. For the most part, like if you understand the concept of Euler integration, every other integration method is similar. All the Runge-Kutta, all the implicit and explicit methods. There's different stuff and there's higher order ways of doing things, but the general idea is like, okay, I know what my current value is. Let me take the derivative, multiply by a time step, and add it to that current value. And I can do all sorts of tricky math to like reduce the amount of error and increase the convergence rate. But that's the general idea. So here it's giving me like an example of Euler method. Let's see what it's giving me. So this one, and this is something that I see sometimes it initializes. This is called initializing the array. And other times it just gives you an initial value and then starts appending values to that array. Personally, I like to initialize arrays, and maybe that's why it's doing it here, because it's reading the work that I had put into it. I find that I have more control over it, and it's a little better in general. And even like this t values, like the fact that we're writing t values into here, that doesn't make sense to me. So I'll show you kind of how I go about this and how I think about it in this case. So I mean, that's for this next step. So first thing to do was calculate this value of k, and there are 2 ways to do it. Well, actually 3 ways if you want to use both ways and then kind of take the average. So I'm going to use Python, create this value of k. I know my T0 is 85 degrees Fahrenheit. My T1 or T45, like 45 minutes later, is now 80 degrees Fahrenheit. My change in time, let me write like a delta t, because I'm going to use dt later, is 45 over 60. And you can use minutes, you can use hours, as long as you're consistent. And that's one thing that I find AI systems are really bad at, keeping track of units. So it's great for a simple math problem like this, but when this derivative is change in Fahrenheit per minute, and over here you're plugging in like 2 degrees per second. It just gets all wacky and doesn't keep track of it well. So it's something that you really need to use your engineering intuition on dealing with it. So I'll say 45 minutes in hours. And then our T ambient is 65 degrees. So K, well, let's write this. dt over dt is the change in temperature. So T1 minus T0 divided by delta T. And let's just take a look at what this gives us. -6 2/3. That value is not going to change. Like, it was a drop in 5, there was a drop of 5 degrees over 3/4 of an hour. And there's nothing I can do to make that more or less accurate. I have 2 data points. There's only one line that I can draw there. That's a fixed value. Now the next step, this is where we have some wiggle room, because I just calculated this left side. Now I need to calculate this right-hand side and divide it. So I'm going to take that dt divided by, and let's put a negative sign here, and it's a negative slope, so we're just going to make it positive, divided by t minus ta. But the question is, what t am I using? Am I using t0? Am I using t1? And the answer to that, it depends on, let's go Zernal, and I should have, so I have a point here, and I have a point here. That's my slope. For a forward, if I want to say that it's a forward difference, like going this way, this is my current time. If I want to say it's a backward difference, this is my current time, and I'm calculating the slope based on the previous value of temperature. So there's forward, there's backward. So if I say that this is my backward difference method, and let's just grab this. This is my forward difference method. They're both a little bit wrong, and they're wrong for the same reason but in opposite directions. One is under predicting, one is over predicting. So one way we can get it to be a little bit better is either take the average temperature between T1 and T0. So we'll come back up here and write this. np.mean of T0, T1. Then I get a 0.38. Or I could take the mean of these two values, and what I'll get is the same thing. I don't like to copy paste this, but we're just kind of demonstrating something here. Normally I would like assign this to a variable, take the mean of the variables, but I just want to show that it's basically the same result. And probably if I take the mean of these two values, I would get the same thing, roughly. That works because there's another method called a central difference method, where the slope is from here to there. I don't know what the temperature is at this point. It's probably the average, but it might be a little bit off. So all 3 of these methods are introducing error, and that's just something that we have to live with. And we'll see where that comes up. So now I need a value of k so I can actually do these calculations. Let's take this one. And I'm just taking that one. Well, I guess I saw most people using backward method. So let's do that one. I'll say that this is k. And you can try all three methods. Are all going to be a little bit different. So it seems like you're getting the hang of creating functions. If you still have questions about that, post it into the Teams group, and we can troubleshoot like how to create functions, how to create doc strings, anything like that. Okay, now let's create, and even here, we could create like a T analytical lambda of T. And this is called an anonymous function. It's a nice, like, simple way of creating, especially things like this, where it's like a math function. So it's a cool way to like condense that the DEF, like the formal definition of a function, and make it one line of code. So we'll say TA plus T0 minus TA times np.exp of negative k times t. So I need a value of, let's do this. I'll define it. So I'm doing this because I just wanted to demonstrate like this definition, your functions, your anonymous functions and your regular functions, whatever the inputs are, that does not need to be defined. It only needs a definition when I actually call this value. So if I want to know like what was the temperature at time 0, it'll tell me 85. If I want to know what the temperature is at 3 hours, it's going to tell me 70.27. Even I could say, what is the temperature at 45 minutes? 79.33. It's wrong. It's not. It should be 80 degrees. And again, that's because we're introducing some error because we assumed that we could use a finite difference to approximate an actual exponential decay. It's okay. Like, we're not off by that much, but it's something to keep in mind. Really what we could do is keep changing k until we get 80 degrees at this point. So right now, what is it? 0.44. So it should be a little bit bigger, right? Or no, a little bit smaller. So 0.38, which was this one, is a little bit closer. 3.9 is a little bit off, so it's somewhere between 3.85, something like that. Pretty darn close. There's better ways of doing this, but we'll save that for module 3, where we're creating like functions that we're trying to solve. But I'll leave this as negative kt, and now we just know that it's off by a little bit. Okay. Now let's create that Euler integration method. I'm gonna, rather than grabbing this code from Copilot and kind of debugging it, I'm just gonna do it from scratch, just so we get some, so you can see kind of the practice of creating these methods. It's not that Copilot is gonna give you a wrong Euler integration. Euler integration has been done 6 billion times. So many people have rewritten the Euler integration functions that, yeah, like it just, there's tons and tons of ways to do it, and there are thousands of better ways of integrating. So writing it out yourself, at least trying it, is helpful just to understand like how these integration methods work. So first step is I'm going to define time. Time is an independent variable, which means I get to choose how long this thing lasts. This is different than like when I have an analytical equation, when we say like time is the independent variable, like it's still a function of time. So it feels like I could invert this and make temperature. Like I could take the natural log of both sides and make temperature the independent value. that's different here because we actually have, coming back up here, we have a differential equation where, again, like time is an independent value. Like this equation is valid for all time. So at any point in time, I can choose 1 hour, and this still has to be true. Kind of a pedantic point, but that's why I'm here, for the pedantics, my scholarly pedantic points, right? So I want to start at time 0, and maybe I want to go to 4 hours, and I want to take n steps. So let's write n. If I want to go every 0.1 hours, I'm going to make it 41. And let's double check. So 41 would give me 0.1 hour increments. 401 is going to give me 100th of an hour increments. We don't really measure. Hours are not a metric thing, so it's kind of weird to talk about tenths of an hour, but 6 minutes. So if I want 6 minute steps. So time is defined. Again, that's an independent variable. Now I can start solving for what are the temperatures. So T, let's say T Euler is NP0's length of time. So I'm saying that for every point in time, there is a temperature. I don't know what those temperatures are, but I want to create a vector that is the same shape as time. When we get to module 3, we'll look at things like maybe we want to know the position and the velocity at every point in time. So maybe we need zeros by length of t and 2. This is why I like to initialize the array, because I get to choose exactly what I want to do. There's no like off by 1 error or anything. So even if I tried to like plot things before I start solving anything, it would help if I imported plot. It doesn't give me anything interesting, but it does at least, it doesn't give me an error because I created T Euler and time to be exactly the same. So before I plot it, let's actually solve for it. The first value of temperature is 85. Well, I could say T0, right? Now for time 1, and I could do it 1 by 1, right? T Euler of 1 is T Euler of 0 plus T Euler of 0 times, well, really I want to plug in this value, negative k times that. So we'll say negative k times minus T ambient. Now if I plot that, it goes from 85 to something and then drops down to 0 because I haven't solved for the rest of the values. And if I wanted, I could do this all one line at a time. I could come in here, say that this is 2. I could come in here, say that that's a 1. And I could slowly kind of populate these values. This is a very long way to do it. And hopefully, if you're watching this, you're screaming at your video saying like, why is he doing it? This is so ridiculous. Just make a for loop. It's like, yes, exactly. That's why we have for loops. So all this stuff we could just do in a for loop. So we set our first temperature. So instead of having this go over and over and over, let's highlight this, tab it over. For I in range, start at 1, go to the length of t. So if I see a 1, I'll change it to an I. If I see a 0 here and here, I'll make that an I minus 1. And now, look at this. Goes from 85, drops down about an hour later. It's 65. That seems really fast. So the thing that's missing here, and maybe you already knew this if you're watching, is that I didn't multiply by any time step. So right now I'm saying just subtract the slope. So this is my current slope. So the default is that it's a slope per hour. But really what I need to do is say times that dt. So I'm taking the change in temperature per time times time is a total change in temperature. Now this looks a little slower, right? And again, it's not 45 minutes is not 80 degrees, but it's not far off. It's about what we'd expect. And I can even plot T and T analytical of T. Let's do K. We'll make that one black. We'll make this one squares. And now I've got this line to say, like, this is where this is what it should look like, and then these blue squares are where I'm actually calculating with this Euler integration. And so some people kind of looked at this and like, oh yeah, looks the same. It has converged. But there's better ways of showing convergence. We kind of looked at those in like this numerical error. Let's just kernel restart run all. And I think it'll pop me down to the bottom. Like in this free fall example, we can see like it's converging, and then we end up with like truncation error. This was a case where I was saving things as a float 32 so that I could look at round off error, but you can't actually see round off error if you're using 64-bit numbers to calculate round off error, because it just gets lost. But we do have this like convergence here where it's like as the number of time steps keeps increasing, it decreases that error. So this is one way that we could do it. Another way is if we did this once. So I saw this a couple of times. Let's merge these two and take all of this stuff, turn it into a for loop. And we'll say like 11, 21, 31, 40. And I'm using like 30 plus 1 so that my delta t values they include the 0 for number of time steps. And then let's go, I don't know, a 101 and 401. And now, because I'm making all these different plots, I got to keep track of them, because now I'll have 1, 2, 3, 4, 5, 6. So let's add a label. And let's capitalize Euler. Poor guy. Did all this work. And you know what? Let's do minutes. I'm just going to take my time step, multiply it by 60, and then I can look at it in terms of minutes, right? That one should work. And I like to add a label for my analytical too. Gets pretty messy, right? I mean, one thing that I can see right away is that these blue squares are farther away than these red square, purple squares. Purple squares are kind of right on top. So it's messy to look at this. Really, all I'd want is maybe like these three. So I can see blue, red, and then yellow is kind of right on top of it. And that would work. And since I'm doing this, I mean, I have this like T Euler. I have it saved for every point in time. I could choose any point in time. We'll make 3 zeros, and then, or let's just make it an empty list, because I'm like this. So I'm going to take the last analytical solution and the last Euler solution and just look at that. Oh, and what did I do? I messed up this because I put this in the wrong spot. Now, and here I'm just kind of printing out the error. There are better ways to look at this, but I go from this last step is off by half a degree, then I decrease time step to 6 minutes, and now it's off by 0.13 degrees. Then I decrease it to 0.6 minutes, and now it's down to 0.01 degrees. So it keeps getting closer to the actual answer. And even if I come in here and put a 1001, now I can see that with 1,000 time steps, now I have 1,000ths or kind of 5,000ths of a degree that it's off. And that's kind of that's what I would expect from these Euler methods, is that if the time step decreases by half, the error decreases by half. Factor of 10 means 10 times less error. So, and again, I could say like plt dot plot, and let's say, what does it go? It goes from 24, 6, 0.6, and 0.24. Plotting it looks kind of weird, so let's do a log. Oh, there's negative errors. Let's look at the absolute value of error. And I think I did it right. So as I'm decreasing that time step, so 11, so it should go from biggest to smallest. Biggest to smallest. So as I decrease time step size, I'm decreasing error. And here, again, I like to have like squares or something to say it's not it might look like a straight line, but there are actual calculated points along there. So hopefully this helped. Oh, and the last thing that I wanted to show was like how we have this function. So we have this Euler method, and if I want to use it to say when is this equal to a certain temperature. And I kind of brought this up earlier, like time is my independent variable, but it can invert this equation and turn temperature, like temperature at a given time, into that independent variable. But it's different for this one because like I need to know how many time steps and I need to know what time in order to figure out the temperature. But that's okay. Like with numerical methods, we can do that. So here's what I'm going to do. All the things that I need here are this Euler integration method. So I just copied and pasted all that stuff. I don't need to keep changing what that n is. So let's say n is 401 because that one seems converged enough. Like it's pretty darn close, closer than we even started with our value of k. So I'm going to go 0 to, and instead of saying 0 to 4, I want to say 0 to, let's call it like time of death. And what I'm going to do is say that time of death is a guess. Let's say that I want to guess that it was 1 hour before this thing happened, before the body was found. So instead of subtracting this, I'm going to work my way backwards in time. So I'm going to add that. So it's just taking that derivative and saying like, okay, if I take one step backwards in time, it's going to add to the temperature rather than subtract from the temperature. I don't need to print that out. So I'm guessing that the time of death is 1 hour beforehand, and now the last value of temperature that I have is 96.2. That's a pretty good guess. I'm pretty close. Really, it should be 98.6. So let's add another tenth of an hour. And now it's 97.6. So maybe 1.3, too high, 2.5. And you might be watching this thinking, like, what, isn't there a better way? Like, how, why is he doing this? Why is he driving me crazy? And there is a better way. And we'll get into like root finding methods, but the general idea is like, once you have something like this set up, what we want to do is turn it into a function. So define TOD calculator and I want to take this last value of T Euler. Okay, so now TOD calculator, open close. So if I give it 1.25, because that's my default value, I'm off by 1.2 degrees, pretty darn close. So if I give it a different value, 1.22, I'm only off by 0.8 degrees. Since I have something that can calculate the error in my prediction, I can use a root finding method from scipy.optimize. There we go. Import fsolve. Fsolve of TOD calculator. I give it an initial guess, so I'll just say 1. I could give it any guess. I could say 1.22 since it's close, but it'll give me a value. And then it says 1.16804,334. That's how many hours before 11 this time of death was found. And it's like, well, is that true? Let's see. So and sure enough, I get that it's within 10 to the negative 13 of 98.6. Again, very, very close to what I'm looking for. So last thing that I saw, and as we're getting here, I'm realizing other thing that people might have questions about is like, what do you mean what time? I told you 1.16 hours before 11 a.m. It's like, well, what does that mean? What time is that? Okay, so well, let's just make a new conversation so it's not. I need a time date calculator that can subtract 1.2 hours from 11 a.m. And here we go. So there are this date time and time delta is a way of doing exactly that. If you want to get and let's copy this code and paste this in here. So I'm starting at 11 a.m. My delta time is TOD time, like that. Oh no. Why? There we go. It just, so TOD time is an array, so I'm just grabbing the value of that array. Just saying like, okay, plug in the actual thing. And here, if I really wanted, I could also ask for, I think %s is seconds. No. Give me the seconds too. Oh, colon capital S. There we go. So I was close. So 9:49 and 55. I think I can say this. So if you're interested, if you were trying to figure out, like, is there a better way to find this time? And that's kind of how we would do it. The 55 seconds is really, I mean, I guess I would round up to 950 at that point, because basically, and again, there are other errors in our calculation, so whatever you want to do with that information. But if you were trying to figure out, can't Python deal with time? Absolutely. It can deal with time. The solution is to import a date time, but the tricky part is using that date time form, because you have to create a date time structure, and then you can use a time delta to subtract time from it. Anyway, it can be a little tricky, but especially with like AI agents that can help us kind of interpret and read through code, that it's a nice way kind of looking at it. All right, hopefully this helps, and I will catch you next time. I'll keep reading through the homeworks. We're on module 2 now, and I'll get back feedback for you.